We could make this epsilon, whatever we wanted, however close to 0 we wanted. But this limit then, as you can see, this changing as I change epsilon, would be a value of n beyond which all of the terms of the sequence were within epsilon of this limit L. So you can see here, if I change the epsilon and make it smaller, then I am moving this n further, but I can get a place where now these dots are the other color because they are within epsilon of this L that we are calling the limit. So we are going to have an epsilon definition here. We can set how close we need to be. We said that we could, if we could get sufficiently close, so we could determine what that epsilon needs to be, and as long as we go out far enough and make n sufficiently large enough so that we are within epsilon of that, then the sequence would have a limit. Okay, let's look at another example. We'll make this epsilon a little larger for a minute so we can see this sequence is kind of jumping back and forth, alternating here. And if we have our n right here, you can see that all of our values beyond that point for the sequence are within epsilon. If I make epsilon a little bit smaller, then I need to move this n out, and I have to move it sufficiently large so that none of these terms in the sequence fall outside of this L minus epsilon bar here. Now let's look at one more, and this particular one we can make this epsilon here, and we see these values are all over the place here, and it doesn't matter where I put this epsilon. If I try and make a limit here somewhere, think it's going to be the limit, I find that terms fall outside of that. So no matter what I choose, I cannot find an n here so that all of the terms after that fall within epsilon of this L. So this is an example of a sequence that does not have a limit. So a divergent sequence. So let's formalize this idea. A sequence A sub n has a limit L, and it's expressed in our notation here, if for every epsilon greater than 0 there exists a corresponding integer n, such that if our n is greater than that n, then the sequence term is within epsilon of L, and that says the absolute value of A sub n minus L then is less than epsilon. So here's a formal definition of that notion that we were just seeing. So it just basically says that we can get n large enough that we will then stay within this if it has a limit. And here's a couple ways to look at it on a number line, or we can look at it like we were seeing on that graph. If we get out far enough here, here's our n, if we let our little n be greater than this n, we always stay within epsilon. And if that is the case, then the sequence has a limit L, and it is a convergent sequence. Now, if we have a function such that if we looked at the function values for all integers and they equaled the sequence values, then if the limit as x approaches infinity of the function is L, the limit of the sequence is also L. And this should be fairly intuitive, because if we have this continuous function that is approaching L, then if we looked at just its integral values of the function, they also would approach L. So this can be useful if we have a sequence that we could also express and get a continuous function that has those integral values equaling that, and if we can find the limit of the function, we've also got the limit of the sequence. Now, since we have this statement, is the converse true? So if we turn it around, is it true? If the limit of a sequence is L, does that mean the limit of a corresponding function is also L? And we have to be careful when we have these theorems about turning them around. Sometimes it may be true, often it is not. Here is an example. So here is a sequence cosine 2 pi n. So if we let n be 1, we have the cosine of 2 pi, which is 1. If we let n be 2, we have the cosine of 4 pi, which is 1. So we can see as we look at these integer values that we will always get a value of 1 for each term in the sequence. Yet if we looked at that as a function and we looked at cosine 2 pi x, we would not have a limit because this would continue to oscillate between 1 and -1. So therefore, the limit of this sequence is 1, but the limit of the function is not. Let's look at another example. We'll use cosine again, but we'll use pi n instead of 2 pi n. Now, as we look at this, we're actually going to start with n equals 0. And if n equals 0, we'd have the cosine of 0, which is 1. Then as we let n equal 1, we get -1. As we let n equal 2, the cosine of 2 pi is 1. As we let n equal 3, cosine of 3 pi is -1. We can see that we alternate. So here is an example of a sequence that does not have a limit because you can see how the terms alternate from 1 to -1, 1 to -1. Let's look at this example with this sequence. It says we're going to start at 1. We're going to have -1/4. And then at 2, we are going to take the term we had, which is -1/4, and we're going to multiply it by -2. So that'll give us 2/4 or 1/2. Then we're going to take that term 1/2 and we're going to multiply it by -2, and that'll give us -1. Then we are going to multiply -1 by -2, and that'll give us 2. And then we're going to take 2, multiply it by -2, and get -4. And also, if we did 6, we'd take that, then -4, multiply it by -2, and get 8. So here's an example of a sequence that diverges. It alternates, but the terms are getting larger and larger. It does not approach a limit. So as we look at this one, we could let n equal 1, and we would have 4 over 2, which is 2. We could let n be 2, and 2 to the third is 8 times 4 over 9. We could plot that, and we could continue plotting these as we let n increase by 1, looking at the integer values here to generate this sequence. And it appears that it's probably approaching a limit, but it's not really obvious. We have to be careful of our resolution when we're plotting a graph to see. But something that we could do is, it looks like it's approaching that limit of 4, but we could confirm that by looking at the limit as x approaches infinity of a function that has these as its integer values. And we know how to do this one because we know that we could take the limit as x approaches infinity, and we could divide numerator and denominator by x to the third. That would make 4 over 1 plus 1 over x to the third. And we know that as x goes to infinity, this is going to go to 0. So we can see the limit for this function is 4. And since this sequence has the same values as integers plugged into this function, the sequence also has a limit of 4. So let's look at what the limit as n approaches infinity of a sub n equal infinity means. And it means that for every positive number m, there is an integer n such that if n is past m, then the sequence term is greater than m. So this means it's unbounded and therefore a divergent sequence. And here is an example. For any m that you pick, I can find an n such that if I picked an integer term greater than that, I'm going to be above my limit m. So if I'm trying to find a limit for this sequence, no matter what I do, if I choose the m to be higher than that, then say, okay, let's move it up here then. Well, then I can move an n over so that as long as I pick this sequential term that is to the right of this, so is larger than n, capital N, I will be above. So that's what it means to diverge. We try and set a limit. We can always find an n such that the terms in the sequence after that go above that supposed limit. So it does not have a limit. We say the limit's infinity, and we say that the sequence diverges.